So to kind of show you kind of what we call a small-scale wind in progress, related to air locating from a high to a low pressure, I'm going to introduce something called a sea breeze, and actually kind of revisit a sea breeze in an upcoming chapter. But we talk about a lot of breezes, and anytime somebody throws a breeze at you, of course they're talking about a wind, and the direction that the wind is blowing is always given in the name. So for instance, when I say sea breeze, the sea is the direction from which it's blowing, is my point. Okay, so sea breeze, the wind, this is a wind blowing from the sea. Where is it blowing? Onto the land. And kind of describe why this happens. But it has to do with the fact, and we've talked earlier, that land heats up more quickly than water. And so what happens, and I have a figure to kind of show you this here in a minute, but during the day, as the sun is high in the sky, the land will heat up more quickly than the water will. And we're going to see that at the surface, at the Earth's surface, that creates that warm air, we said, will be less dense, be fluffy, and have a low pressure. So actually, associated with the land at the Earth's surface, we have kind of an artificial low pressure. And then meanwhile, the air stays kind of cool out there over the seas, over the large body of water anyway. And so that high pressure from the cold air moves towards the low pressure over that's inland. So because the land heated up more quickly. So it's what we call an incoming breeze. And it peaks about 3 p.m. on the coast. Now, if you've ever visited Chicago, you might have heard of something called a lake effect breeze or a lake breeze. And it's the same thing. Lake Michigan, affecting Chicago, is slow to heat up during the daytime. And so it has an artificial then kind of high pressure out there. And the land is fast to heat up, quicker to heat up anyway. And so it has an artificial low pressure. So we kind of have a pressure gradient from, this is my Lake Michigan, and here's my Chicago. Okay, so this is warm, and because it's warm, it's a low pressure, and this is slow to heat up, and since it's cold, it creates a high pressure, and there you go. There's your lake breeze. So here's some pictures kind of go along with what I was just talking about. Before the sun rises, we kind of have this sort of situation where all of the pressures are about the same. Then kind of showing you through the course of the day how the land heats up faster, more quickly to warm, and this stays cool, more stubborn to warm. And because of that, you can see that here at the surface here, we have generally low pressure, and over here we have generally a high pressure. And then this would be our sea breeze. Now notice that we have kind of like a cell sort of situation, because at the upper elevations or aloft, what happens is that actually this kind of warming, faster, relatively quick warming, kind of has air moving up, and it kind of creates somewhat of a high pressure up here. Similarly, over here we kind of have a relatively low pressure. So actually, if we were to look aloft, when we're getting our sea breezes peaking about 3 p.m., actually there is an outgoing breeze aloft and an incoming breeze down here. So at nighttime, we can get a similar phenomenon, and it will give us a land breeze. So remember the word before the breeze, land, means it's coming from the land. So this diagram is kind of flipped around. So what happens at night, so here's my land over here. And here is my ocean or my sea. So what happens at night is that with regard to cooling down, the land cools more quickly. So it'll cool more quickly, and the sea will kind of retain its heat, so now it'll be warmer. And so we kind of have a reverse situation where we have, because it's warmer, we kind of have a low pressure out here at the surface, and because it's cooler, we kind of have a high pressure here. So this would be our land breeze. Okay, and again, we kind of have aloft where we have, over the land where we have a high pressure at the Earth's surface, we have kind of a low pressure up here. And so kind of aloft where we have a low pressure over the sea, we have a high pressure aloft up here. So actually kind of aloft we do have an incoming breeze, but at the Earth's surface we have an outgoing or land breeze. Okay, vertical pressure gradient. Now we're switching gears. That was horizontal. Now this is vertical. So, like I said, you got to kind of remember what vertical means. Vertical means up and down. So here we're going back to this idea. If I was to look at the density of the air here at the Earth's surface, it would be pretty darn dense, high pressure. The air in the same volume up here would be less dense, and it's a relatively low pressure. And so actually this is another what we call PGF, pressure gradient force, okay? And it's going from high to low. So it's called the vertical pressure gradient force. And if this isn't balanced by something else, then actually things would be pretty complicated, because we would have the movement of air, which we call wind. We would have wind basically going from the Earth's surface up in all directions. Okay? And I don't know if you remember, I talked about something called an updraft earlier when I said that in order for precipitation to fall from a cloud, it needs to overcome this updraft. And to me, that's kind of what I think of when I think of an updraft. We do have kind of a gentle sort of cleansing updraft going, but it's generally balanced. And what balances our vertical pressure gradient force, this is the PGF, the vertical pressure gradient force from high to low. What balances that is gravity. And I have went ahead and went out on the internet and got a couple of pictures to show you this. But gravity basically balances the vertical pressure gradient force. Looks pretty messy right there, doesn't it? And we call that ultimately hydrostatic equilibrium. So a parcel of air is neither falling because of gravity, nor is it rising because of the vertical pressure gradient force. In general, parcels of air, now I'm not talking about buoyant parcels of air, but just in general, air does not move because of either a vertical pressure gradient force or gravity. Okay. So I went ahead, and on the next slide I mentioned there are a couple of pictures I got from the internet. See what you think. New slide. Okay, so that would be our vertical pressure gradient force, force of gravity. That's it. This next one I want to show you actually has a parcel of air kind of being hit by the two things. That parcel of air is being hit by an upward vertical pressure gradient force, okay, from high to low. But the reason it doesn't go on up is the force of gravity. And then I like this picture because then there on the side it says that the balance between gravity and the vertical pressure gradient force is what we call hydrostatic. They use the word balance, so hydrostatic balance or hydrostatic equilibrium.